friends, I've made this video for oxygen hemoglobin dissociation curve, and this time I tried something new and I have made this video from my notes, right? So I'll be using my notes to explain your oxygen hemoglobin dissociation curve. Write in the comment section if you just like this way of method, and if you don't like it, also write it. Okay, so let's begin. Now, first thing, I'll be discussing what you need to discuss under the heading of oxygen hemoglobin dissociation curve, right? So so first is, what is it, right? You need to first of all write what is the oxygen hemoglobin dissociation curve. The second is the shape of the oxygen hemoglobin dissociation curve. Then why is it so? That what is the shape? That it's a sigmoid shape, right? So why is it sigmoid shape? Then we have to describe two parts, steep and flat parts, and you have to describe P50%. You have to describe factors that affect curve. You have to describe shift to right and shift to left. And you have to, of course, draw the diagram of oxygen hemoglobin dissociation curve with 4 points exactly correct. And finally, Bohr's effect, right? So let's begin. Now, what is actually oxygen hemoglobin dissociation curve? It explains the relationship between partial pressure of oxygen with percentage saturation of hemoglobin. So the pressure of oxygen affects the percentage saturation of hemoglobin. Now, what is percentage saturation of hemoglobin? The amount of hemoglobin that bounds the oxygen is known as percentage saturation, right? Now, it depends on the partial pressure of oxygen of the blood. So if the oxygen content in the blood is more, then of course the percentage saturation of hemoglobin will be more. That is, the more amount of hemoglobin will be binding with the oxygen. Okay, so I hope you got it, that it is the relationship between the partial pressure of oxygen in the blood with the percentage saturation of hemoglobin, which is the amount of hemoglobin that binds the oxygen. Okay, so let's go to next. We can see that, okay, so as PO2 increases in blood, percentage saturation of hemoglobin increases, right? That is obvious, right? So percentage of hemoglobin bound with O2 increases, right? So next is the curve can also be expressed in terms of volume percentage of oxygen, which is not very important right now. So let's see. And so here on the x-axis we have the oxygen saturation of hemoglobin, and on the on the x-axis we have the PO2, partial pressure of oxygen, and on the y-axis we have percentage oxygen saturation of hemoglobin, right? Okay, so now you can see that it's not linear, right? So first, as PO2 increases, percentage oxygen saturation of hemoglobin also increases, as you can see here, right? But then the curve flattens, and no more increase in PO2 will affect percentage saturation of hemoglobin, which means that in initial phases, if we increase the PO2, partial pressure of oxygen, the percentage saturation of hemoglobin is going to increase, right? But after some point, if we increase the partial pressure of oxygen, it will not affect the percentage saturation of hemoglobin, right? Because it is already 98%, you can see here, right? And 100% is the maximum limit, right? Which cannot be attained, right? And so it is any more increase in the partial pressure is not going to affect the percentage oxygen saturation of hemoglobin. Okay, so the shape is sigmoid shape of this dissociation curve. Now, the second thing you need to remember is two phases. Okay, the first phase you can see here is the steep phase, right? Steep, we know what is the meaning of steep. Steep means slope, right? So you can see it here, which is steep phase. Now you can also see it here, which is a flat, which is also known as plateau. Flat is also known as plateau. So it is a plateau phase, which is flat. Okay, you can see that. Fine. So we have a steep phase and we have a plateau phase. Now let's see why this sigmoid shape occurs, right? Now the sigmoid shape occurred because of hemoglobin affinity for oxygen at various pH levels. Okay, this is one of the reason, and another reason is the cooperative binding of oxygen with hemoglobin. Okay, now this is another important term that you need to remember, that is important, right? So the cooperative binding of hemoglobin of oxygen is that if one oxygen binds with hemoglobin, it will help, it will increase the affinity of oxygen for that hemoglobin. I hope I'm making sense, right? So if one oxygen has bound to hemoglobin, then it will increase the affinity for hemoglobin to oxygen, right? So it will help in the binding of other oxygen molecules, and that's why the shape is sigmoid shape, right? And once it reaches 98%, which is maximum, which can't be raised than that, so it will be flattened, so the curve will be flattened, right? So I hope I'm making sense. So next, so we'll be talking about the steep phase. Okay, so what is the steep phase? Now I can see that steep phase, now this is the same curve that I've drawn. It's the same that I've shown earlier. There's not a very big difference, but it is the same only. Now we can see here the steep phase. Now it is between 10 to 60 mm of Hg. You can see here the steep phase, which is between 10 to 60 mm of Hg. Okay, so this is the steep phase. Now during this phase, even a small rise in PO2 of blood will bring rapid rise in percentage saturation of HB, right? So you can see here that 20, we can take an example 120 to 40. Okay, now I have increased the pressure of O2 in blood from 20 to 40. Okay, so 20, it is almost 20, and at 40 it is 70, right? So I've changed the partial pressure from 20 to 40, but the hemoglobin saturation changes from 20 to 70. Now you can see how vast difference it creates in the percentage hemoglobin saturation. That's why it is called steep phase, right? So what I mean to say is that small change in partial pressure of O2 is going to bring a big change in hemoglobin saturation. That's why it is called a steep phase. Okay, cool. Now what is significance of this phase? As we can see the change from PO2 20 to 40 that I've explained already, right? So thus it facilitates O2 loading in lungs, right? Where small change in PO2 brings rapid change in percentage saturation, right? Now we know that in PO2 this partial pressure of oxygen is going to increase, right? Now as it increases, the hemoglobin saturation also increases, right? Now hemoglobin saturation increases means the O2 content of blood is indirectly going to increase, right? Which is helping in loading of oxygen in hemoglobin, right? So pressure of O2 in blood, which is going to increase in lungs, right? Because lungs is filled with air and the O2 diffuses in the blood, and partial pressure of O2 in blood increases, and hence hemoglobin saturation increases. Thus we can say that it is helping in loading of oxygen in lungs. This is also true in reverse direction. Thus it also helps in unloading of oxygen at tissue level, right? So that's true. Now let's go for the plateau phase. The plateau phase, the curve begins to flatten at 60 mm of Hg. Now as we can see here, 60 mm of Hg, the curve flattens, right? And it almost at 80 mm of Hg, it flattens. Okay, at 60 mm of Hg, the curve begins to flatten, and at 80 mm, it almost flattens. So that's right. So increase in PO2 above 60 mmHg will produce only a small increase in O2 binding, right? Now what is the significance? In hypoxic conditions, if PO2 decreases from 95 to 60 mmHg, as you can see here, 95 to 60, the percentage saturation is not affected, it is constant, right? So if the PO2 of the lungs decreases from 95 to 60, the percentage saturation remains almost constant. So this is a kind of safety factor, right? So if the PO2 decreases from 95 to 60 mmHg, the HB saturation is not going to affect it much, which is a kind of safety factor, right? Now one more important aspect is the P50. Okay, so now what is P50? The level of partial pressure of oxygen at which 50% of hemoglobin is situated is known as P50. Okay, now I'm going to show it here. Here you can see the partial pressure of oxygen at which hemoglobin saturation is 50%, which is normally 27, as you can see here. Okay, so let me repeat again. The pressure of oxygen in blood at which the hemoglobin saturation is 50% is known as P50, right? Okay, so now what is the importance of P50? P50 shows affinity of hemoglobin for oxygen, right? So P50 is inversely proportional to affinity. Okay, and one more thing is that if the P50 increases, you can tell that the affinity has decreased and the curve shifts to right. Now you can see it here that the curve has shifted to right. This is the normal curve. The curve is shifted to right. Now the 50, the partial pressure of oxygen was 27. Now the partial pressure has increased to almost 43 or 44, right? So you can say that shift to right means the P50 has increased. You can see it here, right? Now what this indicates, right, to get the same level of hemoglobin saturation, we need more partial pressure of oxygen. It means the affinity of hemoglobin has decreased. I hope I'm making sense, right? So so you can see here that for the same 50% hemoglobin saturation, we need more partial pressure of oxygen. So the affinity has decreased, we can say that, right? Now this is also true for this is exactly opposite for shift to left, where the P50 has decreased and the affinity of hemoglobin for oxygen has increased. Factors that affect the curve are temperature, pH, carbon dioxide, and 2,3-DPG, right? Now one thing I've shown you here is